Hi everyone. So from this lecture we will try to develop our ideas of calculus on a manifold, and to do that we are going to learn these differential forms, and today we are going to review some background materials that will be necessary for discussing this differential forms thing. As you can see, I have already written some stuff on the screen. That firstly we want to discuss about manifolds and vector spaces, and they will be relevant to define functions and functionals that will play a key role when we try to discuss these differential forms. Then we will go on to tangent space and vector fields, and finally at the end of the lecture we want to talk about something called a directional derivative, and from these places we will see the emergence of differential forms. So let's get started by doing the following. Oops. So first we want to discuss about manifolds. So what is a manifold? That's the first question. So a very hand waving or non-rigorous definition would be: a manifold is such a space that locally looks Euclidean. So this is, though it's not really appropriate to call it a space, but for now to visualize the thing we want to call it a space. This is a space that is locally Euclidean. So what do we mean by this statement? Think of the following. Let's say you have a rubber sheet like this, and if you consider a point, let's say the point P, and you consider a very small neighborhood around P, if this neighborhood is flat, then this is Euclidean. That means there is no ups and downs, no curvatures and all that. So if this is the case for all the points and their neighborhood on this rubber sheet, then this rubber sheet can be considered as a manifold. So this locally Euclidean term is actually coming from the fact that we are considering a neighborhood. An example would be if you take Earth and you consider a very small portion of it, let's say your room doesn't look curved, right? Locally it looks flat. So this is the case for all the points on Earth, and as a result the surface of the Earth can be considered as a manifold. And these manifolds can be of arbitrary dimension. So what do I mean by dimension? If you consider your room, which can be idealized as a cubical box, any point on that room or inside that room can be totally described by 3 points, and those are your very familiar Cartesian coordinates, that is x, y and z. Even though we did not define this yet, but we will define it soon. So when I say that a manifold can be n-dimensional, where n is some number, an integer. It can also be a fraction, but those are really complicated cases and it does not fall inside the category of the topics that we're going to discuss. So for us, this n would mean an integer always. So a manifold can be n-dimensional, and by this we mean that every point in that manifold, let's say P1, it will be completely characterized by some n numbers. and let's call those numbers as x1, x2, x3, dot dot dot, x of n. That means if you want to pinpoint your a point on the manifold, you will need to have n entries. So that is what the dimension means, and typically it is written as, if it's n dimensional and all the entries are real, then it is written as r to the power n. This is what an n dimensional manifold would look like. So this is the definition, or so to say, the informal definition of a manifold. And now we want to discuss another extreme point of view of mathematics. Manifold is one of them. Another one is called a vector space. So for us, knowing the definition would suffice. So what is a vector space? You can think a vector space as a space where all the vectors live in. That's an informal way to think of vector space, but formally what we can say is that if you have a collection of objects, let's say the collection is denoted with some capital P, so collection of objects. Note the word that I'm using objects. I'm not specifying what they truly are, so this is a very abstract definition. If you have a collection of objects, let's say capital V, which includes some objects labeled as V1, V2, V3 and so on. If for any real number, if you have something like this, let's say you take V1 and V2, or you can take V2, V3, or you can take V1, Vn, whatever. You take two of them, you add them together, and the resulting object will also belong to V. And the second property is that if there is some alpha, where alpha is a real number, if you multiply this thing with any V1, V2, V3, whatever, let's call them generally as Vi, this will also belong to V. If you have a set or collection of objects that satisfy these things, then that would be called a real vector space. So this definition will help us in defining vector fields, and later we will define something called an inner product. This definition will help us in constructing those objects as well. So this is the very basic definition of manifolds and vector spaces. Now what we want to do is that we want to define functions and functionals. So you already know about functions, but from the manifold point of view, a function is something, let's call the function f. So this is the function itself, and what it does is that it takes a point of the manifold, let's say an n-dimensional manifold. So this is the manifold, to be precise it's a point, and it maps that point, which consists of n entries, into a single real number. This is how function is defined on the manifolds. And the next thing that we are going to consider, the definition of functionals. So just like functions, we can define functionals for vector spaces, and just like manifolds, vector space can be of n dimension as well. It can even be infinite dimensional. So let's call the functional as some calligraphic f, and let's say it works on a vector space. Let's call that V, and by n I mean this is n dimensional vector space, and a functional would take in a vector or a vector function. In fact, we can even call them a vector function as well, and this will ultimately map this vector thing into a real number as well. Note the fact that we are only considering real vector spaces, so you can also apply an R over here just to be sure that you are dealing with real vector spaces and stuff. So this mapping over the vector space is known as a functional, and you already know the different examples for function and for functional. What you can recall from your high school, that if you had two vectors like this, let's say 2x hat plus 3y hat, and you had p is equals to x hat minus y hat, then if you dotted them, you would get a real number, let's say 2 minus 3, which is minus 1. So this can be thought of as one example of functional, but the very idea of functionals is that it takes in a function and spits out a number. So in that sense, a definite integral would also be a functional. A derivative at some point would also be a functional. So you have already seen examples of functional, but this is the definition that is not introduced in your general first year calculus books. So now what we want to do is that, okay, we are done with the very basic definitions. Now we want to define coordinates or coordinate functions. So let's call it coordinate functions. Note the fact that I have only talked about manifolds and points, and points can exist on a manifold regardless of the coordinate system you choose, because these coordinate systems only help you to describe some certain physical phenomena. However, the points itself, they are not dependent on the coordinate functions. Only when you put a coordinate system on a manifold, then you can relate or use those points to describe some phenomena using the tools of mathematics. So what does this coordinate functions do? Similar to other functions, we'll define coordinate functions as maps that takes points on the manifold and spits out a real number. So we are going to start with the very familiar Cartesian coordinates. So this will be the definition of Cartesian coordinates, and I'll just go with only 3 coordinates. That means these Cartesian coordinates are such functions that if there is some x at a point P, that means this is a function and it's taking a number from the 3-dimensional manifold R3 and it's mapping into a real number. Similarly, y and z can be defined as the same way, just like x. And this mapping for x, y and z are defined as follows. So if there is a point P on R3, by R3 we mean that on the 3-dimensional manifold, such that P is denoted by x1, x2, x3, then under this criteria or this mapping, we have P will be mapped to x of P. That means if P is written as x1, x2 and x3, then acting x, this one, the Cartesian one, over P will result in the following: x1, x2, x3, and it will pick out the first one, the first coordinate, and it will just return you x1. How is that happening? Well, we are defining this x function in that way. Similarly, the y function will pick out the second coordinate, x2, and finally z of P will pick out the third number, that is x3, and this is how you can define your coordinate functions. Similarly, if you go to polar coordinates, the polar coordinates which are just r and theta, that is defined as, if you have some r on r squared, that means a two-dimensional manifold, and it should return you a real number. Similarly for theta, r squared, and then what you have is that there is another real number as well. Now if any point P is denoted over the manifold, r square is denoted by this x1 and x2, right? So R is such a map that when acted on this point, acted over this point P, it takes the entries, both of these entries, and then it squares them, adds them, and finally takes the square root of them. This is how it is defined. Similarly, theta is defined as tan inverse x2 divided by x1. That means the second coordinate goes over here and the first coordinate goes over here. So these are examples of coordinate functions. Now let's move on. Obviously you can do all of this with numbers as well. That is, instead of x1, x2, x3, you could take 1, 2, 3, any real number you want, and you would get some numerical values once you plug those x1 and x2 values into this r, theta, or x, y, z's. So now what we want to do is that, since we are done with discussing manifolds, vector space, and coordinate functions, the next important thing is to discuss about tangent space and vector fields. So for that, again we will make use of this picture. So again, take this point P, but right now let me erase it a bit. So what we're going to do is that we're going to take this point P, let's say this is P, and since this is a manifold and we have already defined functions, what I can do right now is that I can imagine that there might be curves on this manifold like this. So since there are some curves, from our knowledge of single variable calculus, we can imagine that we may be able to draw some tangents over here, right? That means we can differentiate. Obviously these curves have to be differentiable, they have to be smooth. So if we now try to draw a tangent on P, we can do it in many ways, and let me show you how. For example, if you are going from this way to this way, sorry, let me change the color a little bit. So if you're going from this way to this way, that crosses the point P, then you can have a tangent vector like this, right? Now what you can do is that you can also go from this way, that means this arrow, to this way through point P, and you can draw another tangent. And similarly for other directions, you can also go in other directions as well, for example this way. So you can see that on this point you can draw very different tangent vectors depending on which direction you want to travel. As a result, what we have on point P is that we have a set of tangent vectors, not just one tangent vector. So to deal with that set, we have to define the tangent space.